Okay, welcome to module 6. Now in this module we'll introduce the concept of conditional probability. Through this concept we'll study how the occurrence of one event really affects the occurrence of the other event. So we'll in some sense study the dependence between various events. In this module we'll also prove two important theorems of probability theory, which are called theorem of total probability and the Bayes theorem. Now before I introduce the concept of conditional probability, let me take the following example. So you have a box which contains 4 distinct red balls, 3 distinct black balls. So these red balls could be, let us say, B1, B2, B3, B4. These red balls could be R1, R2, R3, R4. 3 distinct black balls, those balls could be B1, B2, B3. What I do is I draw 2 balls at random without replacement from this box. So since the draws are without replacement, the same ball is not repeated in the second draw. And I have to find the probability that both balls are black. So note that in all there are 7 balls, 4 red and 3 black. So this is the distribution of the balls. Now since the experiment has been performed at random, any of the pairs of these 2 balls can occur with the same probability. So if I look at a typical outcome looks like I comma j, where I have numbered these I and j as from 1 to 7. So total number of possible outcomes is 7 choose 2. So I define event A to be the first ball in first draw is black, B to be the event that ball in second draw is black. Then the required probability is A intersection B, which is probability that first draw also I get a black ball, second draw also I get a black ball. So since the experiment has been performed at random, all the 7 C2 choose outcomes are equally likely. So that is the total number of cases in the equally likely probability model. And I look at number of cases which are favorable to A intersection B. A intersection B means I want both black balls. So that means both black balls should come from the collection of these 3 black balls I have. So that can be done in 3 choose 2 ways, because those could be the ball 1, ball 3rd, ball 2nd, ball 3rd, or ball 1 or ball 2nd. So that is those are 3 cases. So that is 3 choose 2. So if you calculate this probability, this turns out to be 1 by 7. Now alternatively, if I look at just probability of A, which is the probability that ball in first draw is black, in all there were 7 balls, experiment has been performed at random, all events are equally likely. So number of cases favorable to A is ball in first draw is black, which is 3. So 3 by 7, that is the probability of A. Then I look at what is the probability that ball in second draw is black, given that the first draw I got the black ball. Now note that once I have the information that the first draw I got the black ball, now there are 6 balls. And 4 are red and 2 are black, because I am given the information that 1 black ball has been drawn in the first draw, but that is not replaced back. If it is not replaced back, that means you have 1 less black ball. So that means 2 black balls, and in all you have 6 black balls. So this probability that probability ball in second draw is black, given that ball in first draw is black, is same as total number of possible cases, which is 6. Number of cases favorable to black is 2. So it is 2 by 6, which is 1 by 3. So this probability can also be written as probability of event B, that means ball in second draw is black, given that the ball in the first draw was black, this probability turns out to be 1 by 3. So if I look at probability of A intersection B, it can be written as probability that in the first draw I got the black ball, multiplied by probability that in the second draw I got the black ball, given that the first draw resulted in a black ball. So that is what exactly 3 by 7, which we got earlier, multiplied by 1 by 3 turns out to be, because earlier we saw that probability of A is 3 by 7. So this is probability of A, and this turns out to be probability of B given A. And this we had already seen, probability of A intersection B is 1 by 7. So what we see is probability of A intersection B turns out to be probability of A, probability of B given A. So if this probability of A is positive, I can divide it by here. So I get probability of B given A as probability of A intersection B by probability of A. Of course, for this to be meaningful, probability of A has to be positive. So it looks like there are reasons to use this formula as a formula for conditional probability. Let us try to give another justification using the relative frequency approach of the probability. So suppose you have a random experiment which has been repeated n times. Now I look at what is the probability B given A. What is a B given A? That means you are given an information that event A either has occurred or is about to occur. So the information is that whatever may be the outcome, it has to be an element of A. So that means total number of favorable cases in this case is FNA, which is total number of cases favorable to A. And what is the number of cases favorable to B? Because I know that outcome is going to be an part of A, so it would be all those outcomes which are part of B as well as part of A. So that is FNA intersection B. So relative frequency of FNA intersection B. So what I do is I can divide it by n both the sides, numerator as well as denominator. This gives me probability of A intersection B, and this quantity gives me probability of A. So this also suggests that this formula is a meaningful formula to define the conditional probability. So now I give this definition. Let A and B be two events. The conditional probability of B given A is defined to be probability of A intersection B by probability of A, provided the denominator is positive. So I have got the formula for conditional probability. Now note that here domain can be omega, power set of omega, or power set of A, both. So I have defined a new set function. Now the question is this set function a probability function? And it turns out this is a probability function on power set of omega as well as power set of A. Let us try to see how it happens. That is what the next result says. So let A belonging to P omega be a fixed event such that probability of A is greater than 0. So my A is fixed. Using this A, I construct a probability function P dot given A. This A is fixed, but this dot may be varying. Then it turns out that P dot A is a probability function for sample space omega. It is also a probability function for sample space A. So what I need to verify to see whether it is a probability function for sample space omega or not, the three axioms I have to see whether those are satisfied or not. So I look at the first axiom, which is about the non-negativity. So probability of E given A is same as probability of A intersection E by probability of E, but this P is non-negative, so this is non-negative. Non-negativity axiom is satisfied. Now let us look at whether it is countable additive or not, or in other words whether probability of union of disjoint events is same as sum of the individual probabilities or not. So to do that, let EI I belonging to S be a countable collection of disjoint subsets of omega. Then you know that if bigger sets are disjoint, then smaller sets are also disjoint, the sets which are contained in that. So if bigger sets are disjoint, the sets contained in them would also be disjoint, that is as it is happening over here. These are bigger sets, they are disjoint, so what is contained in them, they are also disjoint. So if EIs are disjoint, then EI intersection A's would also be disjoint. And this is the fact which I will be using in showing that this probability function is countable additive. So to do that, let us consider probability of union I belonging to S EI given A, which is same as probability union I belonging to S EI intersection A divided by probability of A. As I told before, this intersection is distributed over unions, so I can distribute this intersection over union, so this becomes probability union I belonging to S EI intersection A by P of A. But EIs were disjoint, and EI intersection A were sets which are contained in EIs, and as I told you before that if the bigger sets are disjoint, the sets contained in them would also be disjoint. So that means this suggests that since EIs are disjoint, EI intersection A's will be disjoint, and P is countable additive, so this probability would be same as sum of the probabilities, because P already we know is a probability function. Again, this P of A is a common kind of a thing, so I distribute over each term inside the summation sign, and that is what is happening over here. So this becomes summation I belonging to S, Pi intersection A by P of A. and this is nothing but P of EI given A. That means conditional probability of EI given A. So what you saw from these two is given A, this conditional probability is countable additive. Probability of disjoint unions is same as sum of individual probabilities. Now I have to just verify the third axiom whether probability of whole omega is 1 or not. So P of omega given A is same as P of A intersection omega by P of A, but A intersection omega is same as A, so it is P of A by P of A, which is 1. So it satisfies all the three axioms of probability function, so it is a probability function. When your sample space is omega. Even when sample space was A, countable additivity proof would be exactly the same. Non-negativity follows exactly the same way. P of A given A would be P of A intersection A by P of A, but A intersection A is same as A, so here you get the same thing, P of A by A, which is 1. Now to see few remarks. What we have seen is probability of E2 given A, E2 given E1 we have defined as probability of E1 intersection E2 divided by probability of E1. So if I cross multiply this over here, I get this, provided of course this probability of E1 is positive. Now let's look at what happens in the case of three events, probability of E1 intersection E2 intersection E3. So I combine E1 and E2 together, so these two have combined together, intersection E3. So I can consider this as now two events. By this formula this would be same as probability of the first multiplied by probability of the second given the first. So E3 given E1 intersection E2, it follows from this. Now I apply, these are again two events, I apply this formula again. So this same as probability of first multiplied by the probability of second given first, and this was anyway over there. So probability of E1 intersection E2 intersection E3 turns out to be probability of first multiplied by the probability of second given the first multiplied by probability of third given the first and second. Now you can generalize this to n events. Straightforward. Probability of E1 intersection E2 intersection E1 intersection En would be same as P of E1, P of E2 given E1, probability of E3 given E1 and A2, then probability of E4 given E1, E2 and E3 and so on. So you can generalize this formula in a straightforward manner.